This is Mr. Holsey of H Squared, Sufficiently Understood Science, and today we're going to be looking at speed, velocity, and acceleration, and how to solve the equations that go with them. Now this is going to be a bit of a longer video, so what I'm going to do in the description is I'm going to put timestamps so that you can skip to any area that you're already having trouble with, or something that you wanted to focus on. So some key terms that we need to look at during this tutorial is motion, which is change in position measured by distance and time, speed, which is a rate at which an object moves, velocity, which is speed and direction of a moving object, and acceleration, which is the rate, speed, or directions and the changes that occur with them. So let's start off with speed. Once again, this is the rate at which an object moves. So speed is the distance an object travels in 1 unit of time. And so we're going to take a look very specifically at the triangle that you see out to the right and be able to calculate what that means. So speed, the formula for speed is distance divided by time. So however long a distance that's being traveled divided by the time that it takes to get there. So this triangle will help you solve any speed-related problem. Any speed-related problem. And it's actually really simple to use. Now, the one that you're seeing on your screen right now is a bit of a more advanced version of it, but it's the same thing. So I'm going to draw a simplified version of this triangle. And so what I'm going to do is I'm going to put these units in here, or these values. I'm going to put distance up at the top, time to the left, and speed to the right. Now by using this, I can easily figure out whatever I want. Now since time and speed are across from one another, you put an X there, it means multiply. Since distance is above speed, I would divide. Since distance is above time, I would divide as well. And so if I wanted to know anything here, excuse me, if I wanted to know anything, any one of these, like if I get a question and ask me, how long did it take someone to travel to this location, this far away, at this rate of speed, all I have to do is cover up what I'm trying to find. So if I was trying to find the time that it took, I would cover up time, and that gives me a formula of time equals distance divided by speed. And I could do this for any one of them. The basic speed formula, if I want to know speed, I cover up speed, and that gives me distance over time. So this little triangle allows you to essentially find out what unit or what you're looking for, what the formula is for distance, time, or speed. And so we can see how this triangle works. I have our basic formula, speed equals distance over time, and I can rearrange it using that triangle. So here we go. Distance is equal to time multiplied by speed. So I cover up distance, time multiplied by speed. If I want to know time, we have distance divided by speed. It's a very useful tool to have. Very useful tool to have. I remember doing this as a little kid. I would always be asking how much longer to get to, let's say, my grandma's house, especially my grandma's house. You know, my parents would tell me how many more miles it was. And I was like 5 years old and trying to figure out how much longer it would take. And so they tell me, we're 100 miles from grandma's house. And I'd be looking at the speedometer on their car and they'd be going, 60 miles an hour. And so I'd be dividing in my head, okay, so if it takes 60 miles an hour, it means I go 60 miles in an hour, and we're 100 miles away. I could take that and figure out, okay, so we're a little over an hour and a half from grandma's house. So let's take a little look at our friend Antoine the ant here. So there's a little bug located at 0 centimeters at 0 seconds. And we're going to try to calculate his speed. Right now, he's not moving, so his speed is 0. He's traveled 0 distance in 0 seconds. But 10 seconds later, he's at 50 centimeters. And so we can easily calculate what his speed is. So I'm going to write speed equals distance over time. That's my formula. Because if I did my triangle and I cover up speed, I know it's distance divided by time. And so I'm just going to plug in my numbers. So my speed, I don't know what that is. My time, 10 seconds. My distance, 50 centimeters. And so I can just plug this in right here. And that would give me a speed 5 centimeters per second. 5 centimeters per second. So the speed of the bug is just as distance traveled divided by how long it takes. So 50 centimeters divided by 10 centimeters will give us 5 centimeters per second. So once again, speed is just how fast something is moving. And speed is always going to be a positive number. And when we talk about things that are quantities that can be described as a single number, we call these scalars. So other examples of scalars include things like temperature, volume, mass, energy. If I wanted to know the number of students in a room, I count them. It's one number. And so this is an example of scalars. They give a scale to something that's happening. So we're going to do another example. This is more like what you would see on a quiz or a worksheet or a test. So we're going to go through this problem and figure out what we need to find. So the first step is to read the question, because that's going to tell you what you need to find. So Jeremy ran around the track at the YMCA for 2 hours. Okay, so when he was done, he figured that he had traveled 20 kilometers. What was his speed? So I'm going to box speed right there, because that's telling me what I am looking for. What is his speed? In fact, let's just go ahead and box that whole little phrase right there. What is his speed? Okay, so he ran around the track at the YMCA for 2 hours. I put a very bad T there. I'll redo that. So that's our time. He figured that he traveled 20 kilometers. And there's our distance. So what I'm going to do, just to make sure I know my formula, I'm going to make my triangle. Distance, time, speed. And so it's asking me, what is his speed? So I can mark that out. And I know what my formula is going to be. Distance divided by time. So a really good suggestion when doing any of these problems that we're practicing today is to write out all the things in the formula. So we have speed equals, distance equals, time equals. Those are the things we're going to be working with. And so we already know that we do not know what speed is. So we're going to put a question mark there. Our distance, 20 kilometers. Our time, 2 hours. And so now we know we have speed, distance, time. We've already figured out what our formula is going to be. Speed equals distance over time. And so all we have to do is plug our numbers in. We still don't know what speed is because that's what we're solving for. 20 kilometers over 2 hours. And we're simply going to divide that. Okay, now I'm sure you've already figured out what it is, but I'm going to do it the long method. Okay. So 2 divided by 2 is 1. Bring this down. 2 will not go into 0. It's a 0. And we're done. So our final answer will be 10 kilometers per hour. Because we can't get rid of those units. So 10 kilometers per hour is our final answer. Now let's talk about velocity. Velocity is speed and direction of a moving object. Now there are different types of velocities that you're going to deal with in your academic career. We're going to be doing a simple velocity, an average velocity in this class, but there are other formulas for velocity that you may encounter during your academic career. So keep that in mind. There are some different formulas that apply. So velocity is speed in a given direction. When you know the speed and direction of an object's motion, you know the velocity of that object. Now, quantities that have directions are also called vectors. Other examples of vectors are acceleration, force, momentum, and displacement. So one of the best examples that you would see on a daily basis are weather maps for velocity. So if we have a weather map on the television, often the forecaster will say, well, there's a storm moving 30 miles per hour to the west, northwest, or northeast. Let's go northeast. Okay, and so what they'll do on there is they'll draw, like, so it's moving from Denton here, and they'll draw something on there that looks like this. And it's a prediction of the velocity. So when they say that a storm is moving 30 miles per hour to the northwest, they're giving you that storm's velocity. They're giving you its speed, and they're giving you a direction in which it's moving. They're giving you that vector. And so this is probably the best example of when you see velocity in real life. So the formula for velocity is very simple. It's basically the same thing as speed. You have distance over time. So you can even use the same triangle right here. Distance, time, velocity. Now when you get into bigger, more complex velocity equations in high school, you'll probably see something that looks more like this. And this introduces a very important term that we're going to be using in this class, right here. Delta. So delta means change. Okay, so it's the velocity, average velocity here is the change in distance divided by the change in time. But that's more what you'll see in high school, but it is essentially the same formula. It's just basically speed with a given direction. So let's do a practice problem. So Anne walked 1.5 miles south to her house in 0.5 hours. What is Anne's velocity? So we're going to go ahead and box the question. What is Anne's velocity? So we know we're going to be looking for velocity. Anne walked 1.5 miles south, so we're given the direction. And so this will be our distance. And I'm just going to put an arrow going south right here. That looks terrible. And we have 0.5 hours, which is our time. So we go ahead and make my triangle. Velocity, time, distance. I know I'm going to be looking for, I'm being asked to look for velocity, so I'm just going to mark that out, and that's going to give me my formula here, distance divided by time. So like I said, a good rule of thumb is to write out the components of the formula, velocity, distance, time. And so we don't know what velocity is, so that's our question. Our distance is 1.5 miles, and I'm going to put a little arrow there for south at the moment, or you can put something like that, whatever works for you. I prefer the arrows so you don't accidentally mistake it for, seconds or something like that. And our time is 0.5 hours. So we're going to plug this into our formula. Velocity equals distance over time. .5 miles, 0.5 hours. And so we're going to end up dividing this. Now, a lot of you might be a little freaked out about how to do this problem because you have 0.5, and that seems like it's going to be a bit of a hassle. But what we'll do is we'll put this in a long form for you. So we have 1.5, 0.5. Now, the easiest way to do a problem like this is to multiply these numbers by and multiply the numerator and denominator by actually 10 to get rid of the decimal point. So that's what I'm going to do. I'm going to multiply each of these by 10. And you don't have to do this for all problems. And if you're good with dividing with decimals, you won't have to do this. And I shouldn't be 1.5. That should be 15. So you may not have to do this, but for those that struggle, go ahead and do this. And so we're going to do the basic math here. And so 5 will go into 15 3 times. It's going to give me a 0 there. I have nothing to bring down. And so our velocity is 3 miles per hour south. So our final answer is 3 miles per hour south. And now we get into the tricky one, acceleration. It's a rate, speed, or direction change. Now notice it says direction change, not just a speed change. When we think of acceleration, we usually think of a speed change, but it's also a change in direction. Anytime a car turns, it is accelerating. Even if it doesn't change speed, it's accelerating. Anytime a car brakes, it is accelerating. I know it seems kind of weird. Usually they call it deceleration, but it's just negative acceleration. So here we can actually have a negative number. So acceleration is the rate at which velocity changes. Velocity. Because if you remember, we said that acceleration was an example of a vector. So, and vectors have direction. So here we have any kind of increasing speed, any kind of decreasing speed, any change in direction. So just a little cartoon like visual for you. I highly suggest you draw this out in your notes. It will really be helpful as a visual to show you how acceleration works. So on the top cartoon, we see someone running faster and faster and faster. They're accelerating because their rate of speed, their rate of velocity is going faster. They're speeding up. Their velocity is increasing. We know he has a velocity because they are moving in a direction. In the second cartoon, this is accelerating because the person is slowing down. You have a change in the rate. You still have a change in the rate. So increasing speed, a decrease. Both of those are examples of acceleration. And the third one here, we have a bee flying around. Anytime that bee changes direction, it's accelerating. It's not, maybe not changing the rate, but because acceleration is a change in velocity, not speed. Okay, keep that in mind. It's a change in velocity. Velocity has a direction. And so even though it's not changing the speed of the bee, it is changing the direction. Therefore, it is accelerating because it's a change in its velocity. So the formula for acceleration does kind of intimidate a lot of people because there are a lot of components to it. Well, actually, there's only 3 components, but because you're looking for a change, the formula gets a little bit longer. So the formula is acceleration is equal to delta V over delta T. And so we have this term delta, okay? And delta in math and science means a change. And so essentially what delta is telling us is that acceleration is equal to the final velocity, whatever we end up with, minus the initial velocity, what we started with, over the time final, whatever time we ended our measurements, and initial time, which is whatever time we began our measurements. So it's important that you have all those components. Now, a lot of questions will just say that it moved in 5 seconds or 10 seconds and not give you, the time that it started. So it'd be starting at 0. We're just measuring from 0 to 10. But the reason why you need to know time final and time initial is because you could be asked a question where it gives you the initial time from where it say, for example, it'll say a question where you start at measuring at 3 seconds and end at 15 seconds. And so your total time you'd be working with is 12 seconds. So keep in mind that you have to have all these components. Don't assume. Make sure you read the question. So once again, that's final velocity minus initial velocity divided by the change in time, time final minus initial time, or time initial. So the best way to go about with acceleration problems is to look at examples, to start with examples. So let's go ahead and go through this one. Quinn accelerates her skateboard along a straight path from 0 meters per second to 4 meters per second in 2.5 seconds. Calculate the acceleration of the skateboard. So we're going to box what the question actually is. Calculate the acceleration. Okay. And I'm just going to actually just calculate the acceleration right there, because it doesn't matter if she's on a skateboard or not. So I'm going to just get rid of that. So now we need to figure out what pieces we have. So along a straight path, that's telling us that it's a continuous path, which is good for us in this calculation. So 0 meters per second to 4 meters per second in 2.5 seconds. So we start at 0 meters per second. And so that will be our velocity initial, our initial velocity. Then we have 2 4 meters per second, so that will be our final velocity in 2.5 seconds. And so that's going to be our time final. But you're probably wondering, okay, what's time initial? Well, since it's telling us that it happened in 2.5 seconds, we're going to assume that the time initial is 0 seconds, that we started our measurements at 0 seconds and ended at 2.5 seconds. So what we'll do is we're going to write out all the things to the formula really quick. So we have acceleration, final velocity, initial velocity, final time, initial time. So we don't know what acceleration is. That's what we're going to be looking for. Our final velocity is 4 meters per second. Our initial velocity, 0 meters per second. Our final time, 2.5 meters per second. And our initial time, 0 meters per second. And so all we do is plug this into our formula. We have acceleration is equal to delta V over delta T, which also, so we're showing that change, which is velocity final minus velocity initial, time final minus time initial. So we're just going to plug this stuff in. We're just going to plug this in. Oops. I just realized I put meters per second over here. That's just 2.5 seconds. And so what we'll do is we'll subtract these. 4.0 minus 0 is going to give us 4.0 meters per second. And 2.5 seconds minus 0 will give us 2.5 seconds. So we're about halfway there. So now what we need to do is we need to divide this. Now, because I showed you this earlier, I'm going to do it again, where we have 2.5 into 4.0. And once again, that's a little bit difficult for some people, so what we'll do is we'll multiply the numerator and denominator by 10 to get rid of our decimal points here. So 25 into 40. And so when I do this, I'm just going to go ahead and, so minus 25, because it can only go in one time, right? So that's going to leave me with 15. So here I'll add decimal point, create a 0, bring it down, and 25 into 150. It's going to give me, it'll go in 6 times. And so our final answer is going to be 1.6 meters per second squared. Now, why squared? Because if you notice right here, we already have meters per second, and right here we have seconds. You can't get rid of units. You simply can't get rid of units. And so we have 2 units of time that we have to account for. And so that's why we put the squared. So acceleration is always meters per second squared. Always meters per second squared. So let's do another one. So a car is going 22 meters per second, accelerates to pass, a car going 22 meters per second accelerates to pass a truck. 5 seconds later, the car is going 35 meters per second. Calculate the acceleration of the car. So I'm going to box this, calculate the acceleration. I know I'm going to be looking for acceleration. So right here, car going 22 meters per second accelerates. So we are going to put this in as our velocity initial. 5 seconds later, so here's our time final. And 35 meters now later is going 35 meters per second, so that's our velocity final. Once again, we don't have a time initial specifically stated, so we're going to assume that the time initial is 0. So I'm going to put this over here, acceleration, velocity final, velocity initial, time final, time initial. So my acceleration is the question. My time final, or velocity final, excuse me, 35 meters per second. My velocity initial, 22 meters per second. Time final, 5 seconds. Time initial, 0 seconds. So we're going to put in our formula. Acceleration is equal to delta V over delta T. So velocity final minus velocity initial over time final minus time initial. So our velocity final, 35 meters per second minus 22 meters per second. Our time final, 5 seconds minus 0 seconds. And so when we do our math, we're going to end up with 13 meters per second over 5 seconds. And so let's go ahead and do our math, and we're going to use the long form. We have 5 and 13. Okay, so 5 won't go into 1, but it will go into 13, and it'll go in 2 times, giving us a remainder of 3. We'll create a decimal point, bring down a 0. Now 30. So since we have a remainder of 3, we create a decimal point and bring down that 0. So 5 will go into 30 6 times. And so our acceleration is going to be 2.6 meters per second squared, once again, because we have 2 units of time. So that's our final answer. And one more example. Now this one is something I really want you to pay attention to, because this time we're not gaining speed, we're slowing down. Okay? So it's going to tell us a lot about this problem. It's still acceleration, even though it's slowing down. So an object traveling 200 meters per second slows down to 50 meters per second in 5 seconds. Calculate the acceleration of the object. So we are calculating acceleration, okay? And so we have 200 meters per second, that is our velocity initial, that's where we start at. 50 meters per second slows down to 50 meters per second, so that's our velocity final. And in 5 seconds, that's our time final. Once again, we don't have a specific time stated for time initial, so we're going to assume that it is 0. So we'll put acceleration, velocity final, velocity initial, time final, time initial out to the side here. I really encourage you guys to be doing this out to the side. It makes things so much easier. So we're looking for acceleration. Our final velocity, 50 meters per second. Our initial, 200 meters per second. Our time final, 5 seconds. And our time initial, 0 seconds. So we have our formula. Acceleration is equal to delta V over delta T. Velocity final minus velocity initial over time final, time initial. We're going to plug this into our formula here. Plug our numbers into our formula. So our final was 50 meters per second minus 200 meters per second. 5 seconds minus 0 seconds. So when we subtract all this, we get acceleration is equal to negative 150 meters per second over 5 seconds. Negative 150 meters per second over 5 seconds. So from here, we're just going to do the same basic math. I have 150 in the box, negative 150, and 5 outside of the box. So 5 will go in, won't go in the 1, but it will go into 15 3 times. We bring down that 0. 5 will not go into 0, but we still need to account for it. And so there we go. Our answer, our final answer, is acceleration is equal to negative 30 meters per second squared. Once again, squared because we have 2 units of time. So because it's a negative number, that means it is slowing down. But it's still acceleration. A lot of times, like I said, we'll call this deceleration, but it's still acceleration. Well, I hope you enjoyed this tutorial on speed, velocity, and acceleration. Once again, this has been Mr. Holsey for H Squared Sufficiently Understood Science. Remember to like, share, and subscribe in order to find out when we post new tutorials.